All right. Hello, everyone. I'm Jens Grubert from Coburg University, and I'm your session chair in this session of Handwriting, Controller, and Menus 2. We will have 4 papers in this session, and the first one is called A Comparison of Virtual Reality Menu Archetypes, Raycasting Direct Input and Marking Menus, and the authors are Johann Wentzel, Matthew Lakier, Jeremy Hartmann, Falah, Shazib, Géry Casiez, and Danny Vogel. And Johann, we are looking forward to your talk. Take it away.
Sounds great, thanks. So as mentioned, hi everybody, thanks for coming to my talk today. I'm a PhD candidate at University of Waterloo, and I'm here presenting a comparison of virtual reality menu archetypes, raycasting, direct input, and marking menus. Finish this with the help of my co-authors, Matthew, Jeremy, Falah, Géry, and my advisor, Dan Vogel. So mostly as a commentary on my own attention spans for presentations, I'm going to quickly summarize our findings here. So first, we looked at 108 consumer VR menus looking for design characteristics. We found a huge variety of menu characteristics, and we broke those down into archetypes, comprising 3 different menu styles: linear, grid, and radial. Additionally, these menus have 3 interaction styles, so raycast, direct, and marking. Out of the menu styles we found in the survey, we made 6 menu archetypes that contained either 8 or 24 items. We evaluated these archetypes in 2 studies. The first study evaluated menus at only 1 level of hierarchy, while the second study evaluated 2-level hierarchical menus. There are a ton of design recommendations, but in short, if you're not doing hierarchy, consider using direct input over traditional raycast, as it's often faster. If you're doing hierarchy, consider using a marking menu. Raycast is perceived as easier by participants, even if it's not quite as performant. So here's an example of a menu in a VR application, specifically from the game Onward. Pretty simple, right? It's just raycasting to a group of items hanging in space, placed a few feet away. But here's another menu, this time from the game Lone Echo. It's a scrollable list of items. You've got some buttons on there, you've got multiple layers of UI going on, you've got transparent back panels. It's a bit more complicated. Additionally, this one you have to physically hold and interact with in-game directly. This screenshot doesn't do it the most justice, but you actually even got a little on-body slider you have to toggle to even bring up the menu in the first place. This one has a lot more going on. There's a lot more kind of ways you could kind of have your performance be affected in all these things. Between these 2 menus, it's pretty easy to imagine the trade-offs inherent in their designs. But these are just 2 examples. There are a ton of different UI designs out there with regard to in-game and in-application menus. So this brings us to the research question we chose to tackle in this paper. What are the objective performance and usability trade-offs of today's most common VR menus? So this research objective is split into 3 separate questions. Number 1, what are the most common VR menu design styles? Number 2, how do these menu designs compare in terms of speed and usability? And number 3, how can VR developers use these results to inform their own designs? So to answer these 3, we did 3 separate investigations. First, we did a survey of 108 VR menus to look at common design characteristics. Next, we compared the most common VR menu designs at 1 level of hierarchy, looking for kind of objective and subjective differences in speed and usability. Finally, we did the same experiment with the task modified so that each selection had to be done along 2 levels of menu hierarchy. So let's start things off with the survey. We surveyed a bunch of games and applications for VR. We looked at 108 menus across 84 different applications, which we used Steam charts most popular. We examined a bunch of characteristics, including item layout, interaction techniques, so how to target and choose a given item, selection techniques, so how to confirm your final selection, number of items in the menu, how it's anchored, so the reference frame, like world-based or body-based, levels of hierarchy, and also hand usage. So unimanual or bimanual. On the right are just a few of the games that we looked at, including Population 1, No Man's Sky, Onward, Superhot, Half-Life Alyx, all of the kind of big VR applications that kind of are the most popular ones out there. So across the design characteristics, we found a bunch of different styles. Just for brevity, I'll give you the top 3 from each category. So for item layout, we saw the top three were linear, so just all in a straight line, grid layout, and then radial layout where everything's placed in a circle. For anchoring, we saw that world anchoring was the most popular, then followed by hand anchoring, and then finally body anchoring. For interaction technique, raycasting was the most popular, followed by direct interaction, and then simple hardware button selection. For selection technique, it was most often done with a hardware button. Otherwise, immediate selection or dwell were the most common alternatives. And finally, for hand usage, unimanual selection was most popular, and then bimanual after that. We also broke our survey results down by the most common combinations of menu characteristics. This table shows just the top 10. You can see that a lot of the most common ones used world anchoring, raycast selection, and oftentimes used linear or mixed layouts. But there are some interesting combinations here that we should probably illustrate. So this is our most common menu type. World anchoring, linear layout between 1 and 5 items using raycast selection. Typically, these menus look like the one I showed and the one on the right. It's a simple menu mounted in the world with a pretty simple interaction technique to actually select items. However, there are some other interesting ones. Here's an example of a hand-based menu that uses similar interaction techniques, but actually supports both raycast and direct interaction depending on context. This is in the game No Man's Sky, and actually it's pretty fun because you can actually just poke at menu items because it's all hand-mounted, so it's kind of one of these holographic displays that pops up. It's really fun. It's really versatile in a bunch of different kind of in-game situations. So for the purposes of our study, we took these common design characteristics and designed 6 total menu archetypes. Each of these is a combination of item layout, selection technique, interaction technique, and anchoring. So for each category, we made a version that supported 8 items and another version that supported 24 items, because these are the most common size categories that we found. So on the top, we have raycast selection, has the menu mounted in the world, where you raycast to select, kind of as like most common menus had. Then we have direct selection, where the menus are mounted on the user's hand, and lets you kind of poke at items like in some of the other menus. And then we have marking, which allows us to make swipes in order to select. It's important to note that previous work didn't really examine much about 3D marking menus in terms of kind of comparisons to other menus. We developed a technique for displaying items in 3D space that has less occlusion than typical item placement strategies. So previous ways of setting up 3D menus often rely on this kind of latitude, longitude setup on the right, kind of organizing a sphere of items into a grid of rows and columns. The problem here is with a denser item layout, these rows and columns might start to line up visually depending on your own perspective. And if a menu includes items placed in the back, you can potentially occlude items in that way. But we did is we arranged menu items using what's called a Fibonacci lattice. It's basically populating items in a spiral moving down a 3D sphere from top to bottom. And that kind of almost irregular pattern actually reduces the amount of occlusion based on kind of menu density and overall symmetry. You can see it on the left. The black dots show where items would be placed. So for the first study, we gathered 18 online participants, and we had them do a selection task across all 6 of these menu item archetypes. So essentially, the participants would see a word in their vision and would need to select the icon associated with the word. We tried to keep things really, really simple to focus on pure performance and usability. We measured their time to make each selection, as well as how far their hands had to move when making the selection. And we also measured their subjective responses to the menu designs using the System Usability Scale, or SUS. So here are some general takeaways. Direct input was the fastest overall, and that result was unaffected by menu size. The 24-item direct menu was similarly fast. Marking menus were fast with 8 items, but slowed significantly with 24 items. Then raycasting, it was the slowest, but it received the highest usability ratings, which highlights kind of the trade-offs between speed, performance, and subjective usability between the different menu types. So in terms of general takeaways from this experiment, direct was fastest regardless of the size. Marking was fast, but with this kind of setup, it was slower at 24 items. Raycast was more usable despite being slower. But we're not done. A lot of the menus in the Steam Game Survey included multiple levels of hierarchy. There's previous work that shows that the hierarchy can significantly affect the usability of these menus. So of course, we're going to have to compare the same menus with multiple levels of hierarchy to get a more accurate comparison, which we did. We recruited another 18 participants. 6 also did the first experiment, but based on publication timelines and stuff, this was a year after the first experiment, so we weren't worried about kind of these kind of repeat participants. They did another selection task with all 6 archetypes, but this time the menus were modified to have 2 levels of hierarchy. So they had to select 2 icons in one selection action, simulating hierarchical menu. We have the same independent variables, so time, travel distance, usability with SUS. And I'm glad we did this additional investigation. Once hierarchy was introduced, marking menus actually became the fastest, regardless of the items. So direct input was still good, regardless of numbers of items in hierarchy. Raycasting remains slower, but was consistently still rated as the most user-friendly. These findings indicate that marking menus excel in complex tasks, but might need usability improvements at higher numbers of items. And in this case, lots of times what will happen is, even though the 24-item marking menu was slightly slower, everything else became slower surrounding it. So that kind of slower, larger menu, the kind of speed penalty of that larger menu was kind of surrounded by the rest of the menus. Everything else became slower too. There we go. So there's a lot more to read in the paper, but I'll leave you off with a couple of general recommendations. So implement direct input menus for fast and efficient interaction, especially when dealing with larger item sets. Use raycasting for menus where ease of use and user-friendliness are the main priorities. Opt for marking menus in scenarios with small item counts to take advantage of their performance benefits. Consider user comfort and minimal movement when designing for longer VR sessions, which might make raycasting a good choice. Balance speed and usability by combining techniques. So use marking menus for quick selections in small item sets, and then direct input for more extensive detailed interactions. And also, as your design priorities shift, it might be important to examine a totally different layout because there are objective differences between them. So in short, menu item configurations can significantly change the performance and usability of spatial interfaces. That brings us to the end of the presentation, and now I'd love to take any questions you might have. Feel free to reach out to me or any of my co-authors.
Do we have any questions for Johann? Questions, comments? John?
Thank you very much. That's very interesting. I guess I'm just looking for your comment on, so the sort of in a game scenario, right, consistency is key, right? So you don't want to have to pick up controllers or switch the type of interaction you're doing. Do you have any thoughts on that? And how that might influence particular choice of technique?
Yeah, so at least from my experience, these kind of more physical motion-based menus, into like the marking or the direct input, it's a really nice way to kind of work up this muscle memory. So I think as long as the choices that designers make is consistent based on the situation, I think that the muscle memory is the most important thing. I know in a lot of these games, like switching weapons or switching items and stuff, they have this kind of quick marking selection that is really nice, that you can look over here but not have to actually see what you're doing. I think right now, a lot of developer frameworks and a lot of these kind of tools to build VR games, they still focus a lot on raycast and direct, whereas marking is often a more bespoke way of setting things up. But a lot of the games that have implemented even smaller marking menus have gotten huge eyes-free menu bonuses just from doing so. And I think it would help a lot of these kind of game dev frameworks to also include simple radial or marking menus.
All right, we have time for one more short question.
Per-Ola Christensen, University of Cambridge. I'm just interested in, did you speak to any of these game developers to understand their rationale and their objectives and why they design menus in a particular way? Because they must have thought of something, right?
Yeah, totally. There's a bunch of design considerations. We didn't make speaking to game developers an explicit part of the study, but we did kind of consult with a couple of people, like, connections in our lab that went to more game labs and everything. And we're lucky enough that one of the people on the author team, she works at Unity, so a lot of the stuff that we talked about was based on kind of the Unity XR toolkit and these kinds of things. I think there is a lot more design rationale when it comes to, art style, when it comes to kind of almost the artistic role that one of these menus play, especially when you're talking about, diegetic, like, do they make sense in the world menus, or non-diegetic, where it's just a panel? Like, are you interacting with something as a character versus are you interacting with something as yourself in VR? I think there are a lot of interesting design questions about that, but I think, like, we kind of focus on kind of pure usability, these kinds of things, and we'll leave the artistic choices and the kind of design choices to the designers themselves, I guess, if that answers your question.
All right. So, Johann, thank you again, and let's thank Johann again for this talk. So the next presentation will come from Mark Billinghurst group. The presenter is Zach Zhu, and the title is Evaluating the Effect of Interface Types and Immersive Environments on Drawing Accuracy and User Comfort. And Zach, whenever you're ready, you can take it away.
Yep. Hello everyone, I'm Zach. Today I'm going to talk about my research on the effect of interface type and immersive environments on drawing accuracy and user comfort. The main reason we want to do this project is that because nowadays we have new MR headset that allows users to quickly switch from different immersive environments. The nature of this flexibility could potentially help the users to easily pick up the design tools as they want and potentially help them in the cross-medium design workflow. Another main reason is that some of the previous research has shown how different combinations of input devices could influence the overall drawing experiences in the VR environment. But most of them are based on a single environment and highly rely on the subjective assessment. Now we have some physiological sensors that can help us to monitor the user's muscle fatigue, which could potentially help us to have a better understanding of the user's behavior and experiences in the immersive drawing process. That is why we want to do this research. So in this research, we mainly want to investigate two key features. One is the immersive environment, the other is the interface type. So how do these features influence the drawing accuracy and user comfort, and do they have any interaction effect? This brings us to the research question. How do different immersive environments and interface type affect the performance and usability of immersive 3D object-based content generation tasks? Based on the literature review, we found that there's limited research on designing prototyping across a full reality-virtuality continuum. Additionally, there are few studies about incorporating the drawing tasks into the XR environment. Furthermore, many of these studies on input modalities heavily rely on the subjective measurement, and there is not so many research about employing the EMG sensor to assess the drawing fatigue. That is why we propose 4 hypotheses. We mainly want to explore how environments and interface types could influence the drawing accuracy and user comfort, and whether there is any interaction effect between them. We also want to investigate the correlation between the objective measurement and subjective assessment of drawing accuracy and the user comfort. This is our system design. We choose MetaQuest Pro since it could provide us a flexible choice in terms of the input device and the environment. We used a myo band to monitor users' muscle fatigue, and the second controller was used to track the target object, a 3D printed cylinder. The size and the shape of the object are specifically designed to improve the tracking stability and mimicking the constraint in a real-life drawing scenario. This figure shows the 2 factors in our study, environment and the interface type. There are 36 participants with medium drawing and VR experiences were recruited and be divided into 3 groups based on the environment. Each group of participants will try 3 different types of interface type in the experiment. So in the experiment, basically the users need to perform a raycasting task. They need to draw from both inner layer and outer layer of the cylinder. and each of the strokes has to be completed in one time. After they finish drawing the 2 strokes, participants need to press next trial button. There are 6 trials for each types of the interface. Now let's look at the data logging. For accuracy, we densely sample the spatial coordinates of the tips of the input tools and calculate the equivalent distance between each sample point and the target curve. We also remove the points that are too far away from the target curve caused by the technical glitches to maintain the readability of the data. This figure shows how we filter the data. A total of 1,296 trials of data were recorded and analyzed. For the muscle fatigue, we use a machine learning library to extract and process the RMS value. This is an example of the trend line of average RMS value over time on the outer surface in AR condition. All the data set and code are available on GitHub. We didn't really count the task completion time in this experiment because this task emphasized precision over speed. For the subjective measurement, we use NASA TOX, SUS, SSNQ, and post-study interview. This is a screen recording of the experiment. You can see here the user is drawing in the AR condition, and here the user is drawing in the VR condition, and this is user drawing in the XR condition. About the data analysis, we use a two-way ANOVA and using environment and interface type as 2 independent variables, and we employ HSD for post-hoc analysis when necessary. The evaluation of accuracy and fatigue are segmented into inner and outer wall section due to the different spatial positions of the target curves and the muscle groups involved in the drawing process. Let's first look at the objective data, the accuracy outer. We found the environment and interface type will influence the accuracy individually. Specifically, the AR outperform VR and XR, and 2 hands outperform hand stylus. We have similar results in the accuracy inner. The AR outperform VR and XR. Additionally, the VR outperform XR. Regarding the interface type, the 2 hands outperform both hand stylus and hand controller. About the RMS value, we only find the environment have a significant influence on the muscle fatigue. When the user is drawing on the outer layer, the XR shows higher muscle fatigue than AR. When the users draw on the inner layer, the XR shows higher muscle fatigue than AR as well, and the VR shows higher muscle fatigue than XR. And if we compare the inner and outer layer, compare the accuracy of the inner and outer layer, we can see that the inner layer has a significant higher accuracy than the outer layer. But we didn't find a significant difference regarding the RMS value. About the NASA TOX, we found AR have higher physical demand than VR, and XR were perceived more temporal demanding than AR. The SEO score indicates the hand controller outperformed the hand stylus, and the post-study interview shows across all the environment, the hand controller is most preferred, followed by the hand stylus and the 2 hands. So based on these results, H1 was accepted. We found the users demonstrate significant higher drawing accuracy in AR compared to those in VR and XR. We can infer that the higher accuracy could be attributed to the tangible feedback provided by the real object. However, the physical dimension of these real objects could sometimes become limitations for the drawing tasks. We believe that is why AR is more physically demanding than VR. But this perception contrasts with the objective data on the physical demand measured by the RMS value. And interestingly, the perceived temporal demand in AR was lower than XR, despite we already informed the participant before the experiment that the task completion time will not be recorded. For H2 was partly accepted because we only observed significant effects of interface type on drawing accuracy from both subjective and objective perspective. The 2 hands interface consistently demonstrate higher accuracy than the hand stylus and the hand controller across all the environment. However, the 2 hands was subjectively least preferred interface across all the environment. We believe the higher accuracy of the 2 hands condition can primarily be attributed to the bulkiness of the controller and the stylus, which will create a noticeable gap between the tips and the target curve. And this issue will not arise when the user is drawing with their bare hands. But based on the oral feedback we get, drawing with bare hand are lacks of tangible feedback provided by holding a controller, so subjectively making this method less preferred by the users. The H3 was rejected because we didn't find any significant interaction effect between the environment and the interface type. H4 was partly accepted because we observed differences between some of the subjective questionnaire and objective data collected by the sensors. So based on these based on these findings, we propose 2 design recommendations, one for the UX designers, which is incorporating the tangible user interface elements into the ISMAR content creation interface is highly recommended to enhance the user experiences. For UX researchers, it is worth to explore a broader array of assessment tools that can capture the complete real-time user experiences. We do have some limitations in this work, and we propose the future research directions for these. So the first limitation is that the correlation between the user fatigue and the user's fatigue and the drawing accuracy was observed, but the nature of these relationships remains unclear. So in the future, the researchers should further explore the relationship to clarify the direct effect between the fatigue and accuracy. Second is holding the Quest Pro controller in a reverse position sometimes feel unnatural, so subjectively making the users feel less preferred. So in the future, the researchers should further explore the impact of grip postures on performance and usability when using the same controller with the same shape. Third, our current tasks are still relatively too simple compared to the real-world drawing scenario. So in the future, the researchers can consider engaging the users in a more complex and long-term drawing tasks, coupled with the real-time objective data sampling and analysis. To conclude, our study combined the objective measurement with subjective assessment to thoroughly investigate the effect of various immersive environments and the interface types on the performance and the usability within the immersive 3D object-based drawing tasks. And our research also indicate a disparity between the objective data and subjective assessment, pointing the potential limitations in the traditional subjective questionnaires. That is all of my presentation. Thank you.
So, do you have questions? Wolfgang, you have one?
Wolfgang Stürzlinger, Simon Fraser University. So, very interesting work, and thanks for presenting that. How much of the results do you think are due to the differences in the tracking system? In particular, the hand tracking is most probably different than the stylus tracking.
Oh, yeah, definitely. I believe people, because we did some pilot studies and previous research about comparing hand tracking and the stylus. So the oral feedback we get from the users, most of them prefer to use original or standard controller from the headset because obviously they have better tracking stability. But for this one, in the very beginning, we thought the controller will have a better better accuracy, or objective data, but the result shows actually the hand has a better performance on the accuracy.
Right, and that's one of the issues that I was wondering about, because one of the issues is because you're going on the inside of the ring, you're faced with occlusions. And you're occluding exactly the part of the controller that is used for tracking, whereas the hand model is more robust to occlusion. So maybe what your results, at least a part of your results, is purely explainable, potentially explainable by tracking issues and not by true user preferences. That's why I'm asking.
Yeah, because as I say, the size and the shape of the 3D printed object are designed. So we actually want the users, when they're holding the controller to draw inside the cylinder, we want them to feel some sort of constraint to mimicking the real world scenario. That's why we want to do this. Yeah.
Okay, we have time for one more comment or question, a short one.
Thank you for your talk. I'm curious how you measured the accuracy.
Oh, so the accuracy is, as you can see from here, we use a mathematical formula to generate the curves, to generate these curves, and the users, we densely sample the spatial coordinates of the users, let's say tips. Then we compare the equivalent distance between the tips, between the sample point and the target curve. So then we calculate the mean of it. That's how we get the accurate. That's how we get the representation of the accuracy. Yeah. Thank you.
All right. So let's thank one more time. Thank you so much.
Thank you.
And the next presentation will be an online presentation from Hai-Ning Liang's group. And I apologize if I read out the author names incorrectly. So the authors are Tingjie Wan, Liangyuting Zhang, Yongxing Zhu, Katie Atkinson, Lingyung Yu, and Hai-Ning Lang. And Hai-Ning, you are here at the end if there are questions in the audience. But I think your first author is also available online. And the title is Design and Evaluation of Controller-Based Raycasting Methods for Secure and Efficient Text Entry in Virtual Reality. And if you have been here in the session before, there was also a related paper by Hai-Ning Lang's group, which also looked at secure and efficient text entry. So we're interested in how this goes here. So please play the video. Thank you so much. Do we have some audio? So do we have audio on it? I don't have control for audio. Okay. That would be James in the back. Okay, James, can you give us some audio or? Okay, because I'm not sure whether we are supposed to hear something. So I apologize for not hearing something just yet. Let's see. Now, slowly but steadily. I mean, we're not running terribly late. Maybe we can just replay it from the first slide. That would be great. I heard something, at least. So there is some audio hidden somewhere. Okay, so I mean, I'm not sure if you can fix the audio. That's so you
use variability. Hello everyone, I'm Tingjie. I'm glad to share our work, design and the evaluation of controller-based raycasting method for secure and efficient text entry in VR. In today's digital age, the confidentiality of text is paramount, as sensitive information like personal data, business strategies, and government records can lead to serious consequences if exposed. Real authentication methods like passwords are crucial. They alone cannot fully protect against security vulnerabilities in VR, where devices have sensors that can be exploited to review users' activities, such as typing. Traditional methods like randomizing keyboard layouts can improve security, but often slow down typing speed, impacting the user experience, especially when composing text in VR. In VR, typing on virtual keyboards involves more than just the keyboard itself. It also includes virtual input tools. This opens up a way to improve text security. By introducing variability in those virtual input tools, we can break the direct mapping between the user's action and the control keyboard layout. This enhances text entry security without needing to change the virtual keyboards. It's an efficient and cost-effective approach, avoiding the need for extra protective software or tools. Considering that controller-based raycasting text entry method is currently the most commonly used method in VR, we use this text entry technique to verify our idea, especially when we introduce variability in the direction and set point of the virtual ring. Introducing variability in the starting point of the ring changes the initial point of the ring tied to the controller, leading to different rotation angles for object interaction. This adjustment ensures that even when the same key is selected, the required controller movements vary due to the shifted ring start point. Introducing variability in the ring's direction changes the controller's ring angle, so even when selecting the same case, the required rotation varies. After each selection, the ring's direction is randomly adjusted, affecting the angles needed for interaction. Then we came up to research questions to get the user studies about the evaluation of the proposed approaches. We recorded motion data every time the controller's trigger button was pressed for key selection, temperature, angles, position, and the distance between the keyboard and the controller. Using the algorithms from previous research, we estimated the 3D cursor location and adjusted the 2D keyboard layout accordingly. For password production, we used a tree-based backward inference algorithm to infer typing characters, while for sentence, we clustered keystroke using DBSCN, aligned keyboards using LSE, and marked the keystrokes via KNN. To assess the efficacy and the influence of the two approaches on both security and typing efficiency, we established two baseline benchmarks: a standard keyboard layout and a randomly arranged keyboard. In user study, we defined identical character ratio and symmetric similarity to assess the performance of designed approaches in protecting input contents. Identical character ratio measures how many characters matched between two strings based on their position. Symmetric similarity compares the means of two sentences. To assess the text entry performance, we calculated the entry rate, error rate, usability, and workload. The results showed both the start point random approach and the direction random approach provides text protection comparable to a random layout, whether for passwords and sentence. Although start point random approach and the direction random approach offer faster typing entry rates compared to random layout, they are still noticeably slower than standard layout. Users also noted that start point random approach and direction random approach could be disruptive to typing, which is acceptable for short tests like password, but not suitable for longer text input. Should ciphering a text for text is best during the motion data, but the process of recurring text is different between password and regular text due to the length. Specifically, password prediction utilizes a tree-based backward inference algorithm, as participants consistently conclude their input by pressing the send key. For long sentence, the keystrokes are first clustered. Then the clustering results are aligned with the keyboard, and finally the keystrokes are marked to get the input content. Based on the feature of recurring long sentence, we consider randomly and intermittently introduce variability in the virtual selection tools to improve typing efficiency while ensure security. We named it Introduce Variability to the Start Point and the Direction of Virtual Ring with Random Intermittent Frequency for the ability of protecting and the security of sentence as shown in the two videos. And IDR are not inferior to SPR and DR. For the text entry performance, the The text entry rates of ISPR and IDR are faster than SPR and DR.
Based on
Users'
the
feedback
results
also
of 2 user
confirms that
studies,
ISPR and IDR are
design
suitable for regular tests.
When it comes to test security in VR, it is important to maintain the familiar quarter keyboard to prevent any drops in typing efficiency. Ensuring a smooth input process is also crucial for both improving typing accuracy and providing a better user experience. Our user study showed that introducing variability in the virtual rings at random intervals leads to significant improvements in both accuracy and user satisfaction. Last, security methods should be invisible to users, offering protection without disrupting the typing experience, which ultimately enhances overall satisfaction. This is the share of our work. For more detail, please refer to our paper.
Sorry again for the technical difficulties here. Hai-Ning, you're here to answer also questions. I'm just looking very shortly if we have online questions for the author. No, the author is here, and we have time for 1 or 2 questions from the audience. Please take the opportunity to... That's all right. So, are there questions, comments? Looking, if not, I have a question for you. So, the adjustments that you did using this, let's say, positioning offsets, direction offsets, they seem to be relatively minor compared to what you had in your other works, right? So, relatively minor spatial adjustment, but still the text entry speed dropped off quite substantially, right? So almost 50% lower. And do you have any indications or ideas if people just by learning it for a little bit longer could better adapt to this technique? Maybe you can comment a little bit on that, Hai-Ning.
That's a very good question. So for this particular work, we did 2 studies actually. The first one was, if you look at the video, so for every letter that was selected, there will be a change. Okay, so that decreased the speed compared to using the standard keyboard. Now, for the second study, what we did was that we had we did not change the location of the pointer and the direction of the pointer for every letter, but we used a random factor, okay, to minimize the number of changes. And after we did that, actually the performance went up, and it was very close to the standard keyboard. So by doing just a small change and still making sure that the text entry is secure and cannot be, like for example, the letter type cannot be guessed quickly, we can actually make the text entry speed almost the same as the standard keyboard. So that's why with the second study, where we show that it's actually possible to have more or less a secure way of entering text, yet the speed is comparable to a standard keyboard. Yeah.
All right. Thank you. We have time for 1 more short question, if you want to. Yes, yes, no. If not, then let's thank the presenters again. Thank you so much. And now we're coming to the last paper of the session, presented by Samantha Monti. She's from the group from Marc-Erich Latoschik, and also Florian Kern is a co-author on that paper, and the paper is called Analysis of Immersive Mid-Air Sketching Behavior, Sketch Quality, and User Experience in Design Ideation Tasks. So, Samantha, please take it away.
Thank you very much. Thank you for coming to my talk. My name is Samantha Monti, and on behalf of my co-authors, Florian Kern and Marc-Erich Latoschik, I'm happy to be here. We're from the University of Würzburg. So the ability to convey ideas, mental images, and experiences is vital to human communication. Traditional sketching with a pencil and paper has the power to focus attention and provide simple communication, enhancing problem solving, and encouraging engagement and learning. 3D immersive sketching applications have the unique ability to represent spatial concepts in all 3 dimensions of space, as we would in real life. Studies have found, though, that users require more effort with VR sketching tools than with traditional sketching tools to change stroke detail and to convey the meaning of their sketches to others. The addition of a 3rd dimension contributes to a higher mental task load that impacts creativity and expression during sketching. Prior research has explored various methods to assist users to more quickly and faithfully convey their meaning in sketches. Aurora et al. Found that visual guidance in the form of a grid line pattern or a target stroke assist with depth cues and improve sketch precision in VR, but to the detriment of stroke quality. Barrera-Machuca et al. Described the process of creating 3D immersive sketches as an iterative activity with 4 main steps. Briefly, users decide what to draw in the conceptual design phase. They then move to a planning phase where they observe the sketch from different viewpoints and plan physical actions and hand placements. Next, users create strokes and make edits if a stroke doesn't meet expectations. And finally, users evaluate a sketch in its entirety to determine if the work meets intentions. The process is repeated as users perform high-level edits or rework the conceptual design of a sketch. So we wish to understand if the way in which users approach 3D immersive sketching is task-dependent. We ask, how does user behavior, sketch quality, and the total sketch experience differ when creating sketches to convey ideas than when given a 3D model to copy or trace? To answer this question, we conducted a 2x3 mixed design study. Our between subject independent variable was spatial ability. Prior work suggests that high cognitive demands of 3D VR sketching may affect users with high spatial ability less than those with low spatial ability. Our within subjects independent variable was sketch task, which I'll talk about in just a moment. And the study was conducted with 36 university students. So we used 3 sketch tasks in this study. In the trace task, we displayed a 3D model in the virtual environment and instructed participants to trace the outline of the shape. This task omits the first phase of the 3D sketching process, conceptual design, and allows us to compare base condition, linking what users perceive to how they create 3D mirror sketches. In the copy task, we displayed a similar 3D model and asked participants to sketch a copy of the shape beside it. This task was used to further investigate how users visually encode a 3D model and use this to inform the shape of their sketch. The 3D models here in these tasks contain the same primitive shapes in different arrangements and were selected for their simple components and the likeness to a humanoid robot. Because in the design condition, no model was displayed, and instead we asked participants to design a 3D robot from their imagination. This task moves through all phases of the 3D sketching process. Barrera-Machuca et al. Established a framework for systematically evaluating 3D sketching tools that considers 3 main categories: how users perform the 3D sketching activity, the sketching tools and interaction techniques involved, and the final sketch artifact created. In line with this framework, we evaluate each of these 3 categories. To assess the sketch activity, we consider the total sketch experience with 2 questionnaires. We administer the NASA raw TLX to measure a perceived workload with the mean task load index. And we also developed a sketch experience questionnaire that considers the category system developed by Wies et al. To assess the sketch tool, we measure various aspects of user behavior and sketch technique. We consider where users place their dominant hands in relation to their viewpoints to begin strokes, how much users move their heads between starting and stopping a stroke. And we also consider the efficiency of users and calculate the average time to create strokes, the velocity at which users move their hands when creating strokes, and the ratio of erased, undone, and cleared strokes to the total number of strokes. And to assess the sketch artifact, we ask users to self-evaluate the quality of their own sketches with an immersive sketch quality questionnaire using the category system developed by Weiss et al. For each task, users select one response in each of 4 categories, and the scores are summed to a line precision score. We developed a VR mid-air sketching application that maps mid-air controller motion to generate a tube-shaped procedural mesh. The system features a variety of virtual environments, but to avoid the confounds of spatial references during the study, participants were presented with a white illustrative environment. We conducted the study with the HP Reverb HMD and rendered models of the Reverb controllers with the sketch tip added at the front. So let's get to the findings. For the sake of time, I'm only going to present some of our findings. We found a significant main effect of sketch task on the mean HMD movement during a stroke. Users moved their heads more between starting and stopping strokes in the design condition than they did in the others. Head movement allows users to rotate a sketch to a view parallel to the body, to uncover areas obscured by the arm and controller, and to make it easier to assess depth and the direction of travel. Van Summers indicates that a clear line of sight is important in tracing tasks, but not imperative when sketching an empty space. But we found that users worked more to improve their vantage point when sketching an empty space without the benefit of a reference model. We also observed a main effect of sketch task on the ratio of redacted strokes. Participants performed more erase, undo, and clear actions in the design condition than they did in the others. We believe that users made strokes to explore ideas, to visualize different options, and try out possibilities of design. And we suggest that these strokes are not always made in vain, but rather contribute to the creative process by providing immediate visual feedback of the 3D shape. In general, we found no effect of sketch task on the overall sketch quality rating, but we did find that sketch task influenced one aspect of sketch quality, and that was the rating of line straightness. Participants rated the straightness of lines in the trace condition higher than those in the copy condition. This suggests, however, that linear accuracy contributes only a small amount towards sketch quality. We discovered no significant main effect of sketch task on the task load from the NASA raw TLX, but we did find that it affected one question, and that was temporal demand. During the completion of the task, participants rated the time pressure as less demanding in the design condition. And we found no effect of spatial ability on the mean sketch experience ratings, but again, we have one question that was standout, and that was the ease of start rating. Participants ranked the ease of starting lines in the design condition higher than in the trace condition. We also found that there were 3 variables that correlate to the subjective sketch experience. We observed a moderate negative correlation to line precision. So the higher that participants rated the quality of the sketches, the poorer they reported their sketch experience, suggesting that when users focus on precision rather than expression, the total sketch experience diminishes. We found that as users redacted more strokes, they rated their total sketch experience higher. Again, we believe that some strokes are essential preliminary strokes that contribute to the creative process, allowing users to visualize the 3D shape in midair and to try out possibilities of design. We also observed that as perceived workload increased, users rated their sketch experience lower. And finally, as participants moved their heads more while creating a stroke, they redacted a greater percentage of strokes. So back to our research question. We asked, how do user behavior, sketch quality, and the total sketch experience differ by sketch task. In other words, is 3D immersive sketching task dependent? The answer is yes. We found that when creating sketches to visualize and communicate one's own ideas to others, as opposed to copying and tracing models that were designed by somebody else, sketch efficiency, sketch technique, quality, and the sketch experience change. So what does this mean? Well, if we want to develop methods to truly assist users to more quickly and faithfully convey their meaning in sketches, we need to accurately understand how users approach sketching their own ideas, not just tracing or copying 3D models. Evaluations of 3D sketching systems need to include in conditions with design tasks to clearly understand how users genuinely interact with the system so that we can exploit natural user behavior. We note two limitations of this study. First, we had only one left-handed participant. And second, we didn't restrict the sketch size in the design task. This allowed participants to create sketches of any size. And depending on the size of the sketch, a user may employ more head movement to create longer strokes. It would be interesting to investigate head movement in design tasks when sketch size is constrained. This is just a first step towards understanding the mechanics of user behavior in 3D sketching tasks, and we feel that a more detailed analysis of the basic aspects of 3D sketching behavior would be a valuable contribution as a follow-up study. Some references for you, and feel free to scan to find out our other results. Thank you.
Great. So let's thank Samantha again. So we have time for one or two questions, comments. I'm looking into the audience. John?
Thank you very much. That's very interesting. So in your task, was it just the robot that they were having to do?
Right. So they copied or traced the models, and then they freely designed or sketched their own robot.
Okay. Mm-hmm. We did some sketching work a while ago, and one thing that we noticed is performance was quite different between like regular shapes, like things that would involve rectangles, or things that involve circles, right, which are a bit harder to produce. Did you have any observations on that? We
had several comments towards it. So you can see in the tasks that we have a sphere. Let me find the slide. And it was interesting to see how people approached drawing this sphere. We also had a cone. These circular shapes are very difficult for people to draw.
All right. Are there more questions? We still have 3 minutes in the session. If not, just a short question. So you reported on the temporal demand differences in your TLX measures. Mm-hmm. Do you have any idea what's the underlying potential cause of that?
Yeah, so I had some thought about that. In both of these copying and trace conditions, the end goal is set, and meaning that they had to complete each of these lines to complete the task. But in this design, I don't know what the end goal is. Nobody else knows except for what their head is. So I think that they felt freer to stop at any point.
All right, great.
Thank you.
So, Samantha, thank you again. So let's thank the author again. And this brings us to the end of the session. And I wish you a good lunch, great conversations, happy networking, and thank you again for being here today.